In the 21st century, India has witnessed huge technological developments across all sectors. Yet even today, all economic and societal applications of strategic importance like agriculture, disaster management, defense operations, energy, and tourism are heavily dependent on accurate weather predictions. The National Center for Medium-Range Weather Forecasting is a center of excellence in weather and climate modeling under the Ministry of Earth Sciences. The mission of the center is to continuously develop advanced numerical weather prediction systems with increased reliability and accuracy over India and neighboring regions through research, development and demonstration of new and novel applications, maintaining the highest level of knowledge, skills and technical basis. Ministry of Earth Sciences has acquired high-performance computing facility, total of 6.8 petaflops, which has been installed at two of its constituent units, 4.0 petaflops HPC facility, named Pratyush at Indian Institute of Tropical Meteorology, Pune, and 2.8 petaflops facility named Mihir at NCMRWF, Noida. It also improved India's rank to 4th position in the world in terms of dedicated HPC resources for weather climate forecasts, as per Top 500's January 2018 ratings. Mihir is India's second fastest supercomputer, with 2.8 petaflops of peak performance, powered by Intel Xeon Broadwell CPU, and has total storage of 6.3 petabytes. It has Intel KNL70-10 nodes with a peak performance of 31.92 flops.
I am Dr. Praveen Kumar D, Scientist G, working at NCMRWF, Ministry of Earth Sciences. I look after the HPC infrastructure at NCMRWF. Today at NCMRWF we have a 2.8 petaflop high performance supercomputer, which is basically from the Cray OEM. This machine was procured in the year 2018, and since 2018 we have made considerable progress in our forecasting capabilities. Today NCMRWF runs a 12-kilometer global ensemble forecast system, which is the highest resolution ensemble forecast system in the world. And we have plans to upgrade this supercomputer again in the next till 2025. The plan is to go to a 150 petaflop system by 2025, and this will be an augmentation of the current computing system in a phased manner. So this machine basically caters to the operational commitments of not only of NCMRW but also IMD and INCOIS. So this machine, this 2.8 petaflop machine, which put together with the machine installed at IITM, amounts to 6.8 petaflop system, and this is the highest computing power available in the country dedicated to weather and climate application.
Mihir is housed in a badminton court-sized room at NCMRWF, Noida, and is capable of performing jobs equivalent to more than 2,500 high-end laptops, all working in tandem. The high-performance computing system will provide facilities for improving weather climate forecasts. It is the country's largest HPC facility in terms of peak capacity and performance.
Yeah, my name is Ashish Kumar Mitra. I am the head of National Center for Medium Range Weather Forecasting. This is part of Ministry of Earth Sciences, and we are responsible in this center for developing models for weather and climate prediction. So these models are called numerical models. So we gather all the observation data through the internet from different agencies. It contains radar data, in situ data, and also satellite data throughout the globe, whatever is available. It comes to this center within half an hour, and all this data is assimilated into these numerical models. And these numerical models, they are basically the governing laws of the atmosphere. So atmosphere is like a fluid, so there are waves, so they are represented by dynamical laws of the atmosphere, fluid dynamics laws, and there are physical processes happening like cloud, radiation, boundary layer, land surface processes, orography interacting with the wind. So all these physical processes in terms of mathematical equation are built into this numerical model. So all these processes are, as I said, dynamics and physics. They basically contain the total part of the model, and they are programmed using computer language. It could be Fortran, C or Python, and they are all run in parallel processor, what we call supercomputer or high performance computers. And you need a lot of computing power, because these mathematical equations, they are partial differential equations, and they are solved numerically. And what we do, we divide the whole globe, and the atmosphere is, let's say, considered up to 70 or 80 kilometer up. So the three-dimensional atmosphere is divided into grids. So you have to do computation at each grid point, and so there are multiple number of points. So the dynamical equation, the physical process have to be computed at each grid point, 3 dimension in the atmosphere. So you can resolve the atmospheric waves, physical process, what is happening by numerical methods, what I said earlier, partial differential equation, the physical process. So it takes enormous amount of computer time. And suppose we want to predict based on today's weather, what will happen tomorrow. So again, the time is also divided into intervals. So generally we divide the time, 1 hour is divided into, let's say, 6 minutes interval or 3 minutes interval. So again, this computation has to be done at each 3 minutes interval, so that you can catch the atmospheric waves and the physical process, what is happening. And that's what we call simulation. So there are many engineering or science problems which are done on supercomputer. We call it simulation. So here we simulate the weather and climate using these governing laws of dynamics and physics. And as I said, the globe is divided three-dimensionally into many grids, and time is divided into, let's say, fraction of minutes. And let's say the time interval is 3 minutes. So let's say when a cyclone is approaching, we start seeing the cyclone in the Bay of Bengal, and it's likely to come and hit Indian coast after 5 days. So we have to make a prediction for 5 days, let's say. So we have to define what is happening today over, let's say, Andaman Seas, the cyclone is formed, and use these models and this observed data. So all the observed data will define today's weather condition, again in 3 dimensions, and you use this model equations to integrate. We call it time integration. So this weather prediction mathematically is a mixed initial boundary value problem. So you define the initial condition today and try to solve this numerically, these equations, and go ahead, do the time integration up to 5 days, or you can do it up to 10 days. If you do it, let's say, up to a season, it's called a seasonal prediction. If you do it for centuries, it's climate prediction. So these are different scales what we are interested. So we select the model accordingly, the parameters of the model. If we are interested in a very severe weather like cyclone, which can be predicted, let's say, 5 days in advance, so we focus on very high resolution, the grids are very fine, and all the physical process, I said, convection, boundary layer, cloud, interaction with orography, solar radiation, they are all computed very frequently and in fine resolution, so that the severe weather like cyclone or, let's say, heavy rainfall or a thunderstorm can be captured very well. So that's why if you want to predict, let's say, a season in advance, what will happen to the monsoon, let's say in the month of May, we want to all know the monsoon will be normal, above normal or below normal. So again, you use this numerical model, you define the initial condition, but the difference is when you want to predict anything beyond 10 days, you need to include the ocean also. So it has to be a coupled model. So only atmospheric model will not work. So whole of the ocean going up to 5 kilometer deep, everything has to be included in the model. So your computer time again increases. You need more computer time. So it becomes an atmospheric ocean coupled model. So more and more computation is required. Along with atmosphere, you have to compute ocean, and what is happening in the ocean, you have to pass it on to the atmosphere. What is happening in atmosphere has to be passed on to the ocean. So all this thing will define the coupled system, how it is evolving with time. Then if you run this model for a season, let's say 4 months, again you divide this into time interval. So you get a seasonal prediction of monsoon.
Mihir High Performance Computing Facility will improve following services. Weather forecasts at block level over India, which can predict extreme weather events. High-resolution seasonal and extended range forecasts of active and break spells of monsoon. Very high-resolution coupled models for prediction of cyclones with more accuracy and lead time. Ocean state forecasts including marine water quality forecasts at very high resolution. Tsunami forecasts with greater lead time. Air quality forecasts for various cities. Climate projections at very high resolution.